In today's lecture, we will be covering main group chemistry, the P block, specifically groups 16 to 18. In the last two lectures, we covered the S block and the first half of the P block, so now we will finish this section of the course by looking at the second half of the P block. So that would be groups 16 to 18. Starting with group 16, also known as the chalcogens, this group contains mainly nonmetals with the metalloid tellurium and the metal polonium. So the nonmetals include oxygen, sulfur, and selenium. The general electronic configuration of group 16 is noble gas Ns2, Np4. Common oxidation states include -2, +2, +4, and +6. The +6 oxidation state is rare for tellurium and not seen for polonium. Group 17, otherwise known as the halogens, contains only nonmetals which display a variety of physical states. Here is a list of the halogens, and they have the general electronic configuration, noble gas Ns2, Np5. Common oxidation states include -1, +1, +3, +5, and +7, although fluorine is a big outlier and will be explored separately from the rest of the group. The last group we will look at are the noble gases, which are all nonmetal gases as the name implies. Group 18 includes helium, neon, argon, xenon, and radon. Their general electronic configuration is noble gas from the previous row, Ns2, Np6. Helium is the only exception with an electronic configuration of 1s2. Common oxidation states for the noble gases are 0 and pretty much nothing else. We will start our in-depth coverage of group 16 elements with oxygen. Oxygen has two main naturally occurring allotropes, dioxygen gas, commonly just referred to as oxygen gas, as well as ozone. Both dioxygen and ozone are oxidizing, but ozone is significantly more oxidizing, which we will see on the next slide. Just to show you how oxidizing dioxygen can be, here is a redox reaction with methane. Notice that the enthalpy of the reaction is very negative, indicating that this reaction is very thermodynamically favorable. This is actually the reaction that occurs when you burn methane in air. Similarly, most hydrocarbons, sugars, proteins, etc. undergo very favorable oxidation reactions with dioxygen. If this is the case, why don't we burn up in air? We are made up of compounds that react very favorably with dioxygen. The reason why we don't spontaneously burn in air has to do with the electronic structure of dioxygen. If you look at the molecular orbitals of oxygen, you can see it has two unpaired electrons in two degenerate pi star orbitals. This means dioxygen exists in a triplet state. What I mean by this is you can have three possible electronic configurations for the unpaired electrons. You can have up, up, down, down, and up, down. These two, down, up, are essentially the same. So you have three possible electronic configurations. If you actually cool down air with liquid nitrogen, you can collect liquid oxygen as shown on the graphic to the right. It is a blue liquid that is attracted to magnetic fields due to its unpaired electrons. Because oxygen is in the triplet state, the oxidation of hydrocarbons, sugars, etc. is kinetically unfavorable. This is because the reaction ends up being spin disallowed. Spin needs to be conserved in reactions, and if you look at the oxidation of methane using dioxygen, you can see you go from a singlet and triplet reactant to two singlet products. As such, when oxygen attempts to react with singlet reactants, like methane or sugars, etc., there's a huge kinetic barrier. That's why you need a spark or flame to begin combustion reactions. If spin needs to be conserved in reactions, then how do combustion reactions even happen? One way is if the singlet reactant forms a radical species through bond breaking, which would require a lot of energy, so that's your spark or your flame. The other way is if triplet oxygen converts to singlet oxygen, which is much less stable due to the pairing energy of the pi star electrons shown right here. Think of singlet oxygen as an excited state of triplet oxygen, which can be accessed through the input of energy. Once formed, singlet oxygen either reacts with something or it relaxes back down to the more stable triplet state. In the singlet state, however, dioxygen is much more oxidizing because it can react with singlet reactants without a large kinetic barrier. When looking at ozone versus dioxygen, I mentioned that ozone was more oxidizing. This is supported by the reduction potentials of the two allotropes, where ozone has a much higher reduction potential, 2.07 volts versus 1.23 volts. The reduction potential for ozone is so high, in fact, that ozone doesn't form under normal conditions, generally in the upper atmosphere or when there is an electrical discharge. When looking at oxygen-containing compounds, they're generally formed through oxidation reactions. In addition, oxygen more commonly forms covalent bonds, but it can also form ionic interactions. Due to oxygen's high electronegativity, though, second highest in the periodic table, it is almost always in the -2 oxidation state with a few exceptions, such as hydrogen peroxide and oxygen difluoride. Oxygen generally forms two bonds with two lone pairs, so it can act as a Lewis base. Oxygen donors are considered hard Lewis bases due to the small size of oxygen and its electronegative nature. If you look back at the previous lectures, we have already covered many reactions of dioxygen as an oxidant, similar to this reaction where zinc is being oxidized. Ozone can also act as an oxidant, generally producing oxygen as a byproduct. Anionic oxygen compounds, such as oxide or O2- in zinc oxide, often act as strong Bronsted bases in addition to being Lewis bases. Oxide can deprotonate water to form two hydroxides, which themselves can act as Bronsted bases. I will assume you're comfortable with organic compounds containing oxygen, such as alkoxides, ketones, carboxylic acids, etc., as well as polyatomic anions, such as sulfate, nitrate, phosphate, etc. There are other forms of oxygen and oxygen-containing compounds that are very reactive, such as superoxide, but these generally involve unstable radicals and are beyond the scope of this course. Now moving on to row 2 of group 16, elemental sulfur exists as several allotropes that are yellow in color. The specific allotropes of sulfur are cyclic in nature and vary according to the number of sulfur atoms in the ring. The structures shown below, S6 to S8, are the most common. Based on the reduction potential, you can see that sulfur is much more reducing than oxygen, and as such can react with oxygen to form sulfur dioxide. This reaction requires the input of a large amount of energy, even though it's exothermic, so elemental sulfur is stable in air under normal circumstances. Common oxidation states for sulfur include -2, -1, +2, +4, and +6, in comparison to oxygen, which is mostly -2. In many ways, sulfur reacts similarly to oxygen and can be considered an oxygen analog, but keep in mind it is a much softer Lewis base. Sulfides and hydrogen sulfide are Bronsted bases, much like oxides and hydroxide, but with smaller pKa values, so they are much less basic. This makes sense because H+ is a hard acid, and sulfur is softer than oxygen. Why does dihydrogen sulfide form then if hydrogen sulfide is not as strong a base as hydroxide? It's because H2S is a gas, and the reaction is driven to completion according to Le Chatelier's principle. Because sulfides are softer anions, they tend to be better nucleophiles, and they readily undergo substitution reactions. This reaction here shows hydroxide's greater basicity, as well as sulfur's greater nucleophilicity. The hydroxide deprotonates the thiol, generating a thiolate, which then undergoes a substitution reaction with Rx. Disulfide bonds, which are common in biology and proteins, are an example of sulfur in the -1 oxidation state. Looking at some reactions with sulfur, we can see that the lone pairs can be sequentially oxidized to give a sulfoxide and then a sulfone. The lone pair on sulfur dioxide can also be oxidized to give sulfur trioxide, which then reacts with water to form sulfuric acid. Because sulfur is less oxidizing than oxygen, sulfur-sulfur bonds are much more stable, although they are prone to reduction. You may also notice that sulfur can form double bonds with itself. Why is this? It's because sulfur is even smaller than phosphorus, so its p orbitals can overlap to form pi bonds. Sulfur can also form 5 and 6 coordinate compounds, usually with halides like fluorine. Sulfur hexafluoride is a gas that is extremely dense and can be used to make your voice go very deep. You shouldn't really breathe it in, though, because it is difficult to expel from the lungs. You often need to hang upside down to get rid of it. Moving on to selenium, it has several allotropes in its elemental state, including red, black, and gray forms. Red selenium can be either amorphous or crystalline, and it is comprised of cyclic selenium-8 units. Black selenium is a mixture of cyclic polymers with up to 1,000 selenium atoms possible, while gray selenium is crystalline with helical selenium chains. Selenium is even more reducing than sulfur, as shown by this reduction potential, which means selenium in the -2 oxidation state is much less stable. Selenium displays very similar chemistry to sulfur, except that the +2, +4, and +6 oxidation states are more prevalent due to its more reducing nature. As shown here, selenium can be oxidized much like sulfur, but this reaction is even more thermodynamically favorable. A big difference, however, is that selenium trioxide is less stable than sulfur trioxide, so it undergoes a disproportionation reaction, that is, it undergoes a redox reaction with itself to form two separate products. Looking at some reactions with selenium, the similarities with sulfur become more apparent. Selenium can form hexacoordinate species, generally with halides like fluorine. Selenium dioxide reacts with hydrogen peroxide to form selenic acid. This is a little bit different than sulfur because selenium trioxide is not stable. Group 12 transition metals, so zinc, cadmium, etc., react with selenium to form selenides. I didn't show this earlier, but the exact same types of reactions occur with sulfur as well. The organic chemistry of sulfur and selenium are also similar, in that the lone pairs of both selenium and sulfur can be oxidized. I've only shown the first oxidation of selenium here, but further reaction with hydrogen peroxide is also possible. Speaking of organic chemistry, carbon-selenium double bonds are possible, but quite rare due to the large size of selenium. But carbon-sulfur double bonds are known. Contrast that to silicon and phosphorus, which are larger atoms and don't form double bonds as easily as sulfur does. Moving away from the nonmetals, we encounter the only metalloid of the chalcogens, tellurium. It is a silvery white metal with a structure similar to gray selenium. It acts as a semiconductor when exposed to visible light. Looking at the reduction potential of tellurium, can you guess which oxidation states are the most common for this element? Since tellurium is more reducing than even sulfur and selenium, it generally only adopts positive oxidation states. Why isn't plus 6 as common? This is due to the inert pair effect. Tellurium is a fairly heavy atom, so the 5s orbitals are more inert than might be expected. Here is a rare example of tellurium in the -2 oxidation state upon reacting with zinc metal. It should be noted that materials made from group 12 and group 16 elements are popular mixed semiconductors, much like the materials made from group 13 and group 15 elements. Mixing these species together allows you to tune the band gap of the semiconductors, and you can also have 3, 4, 5, etc. component systems like zinc, cadmium, telluride. More commonly, you'll see tellurium acting as a reductant, especially when reacting with halides to generate 2-coordinate and 4-coordinate species. Tellurium will also react with dioxygen to form tellurium oxide. Only reactions with highly oxidizing fluorine will yield 6-coordinate species like tellurium hexafluoride, where it adopts the +6 oxidation state. With respect to polonium, the only metal in group 17, it is a radioactive metal that has a relatively short half-life, 140 to 50 days depending on the isotope. Various oxides and halides are known, but we won't really be covering polonium in this course because not much chemistry has been done with it because of its radioactivity. The second last group we will look at is the halogens, or group 17, but we will address fluorine separately because it is quite the outlier when compared to the rest of the group. Fluorine, in its elemental form, is a pale yellow diatomic gas. Fluorine is the most electronegative element in the periodic table, and elemental fluorine is one of the strongest oxidants known. Fluorine also has a very high electron affinity and a very high ionization energy. As such, fluorine only adopts the -1 oxidation state. Additionally, because it is so small and charge dense, fluoride is a hard Lewis base. We will see how this differs from the rest of the halogens. Fluorine forms very strong bonds with silicon and carbon, which means those bonds are very difficult to break. If you have a compound that decomposes through a CH bond being oxidized, a common trick is to replace that bond with a more stable CF bond, which will be more resistant to oxidation. Moreover, polymers like Nafion and Teflon, which are very chemically inert, are perfluorinated versions of polyethylene polymers. This reaction here is just showing the oxidizing power of fluorine gas. It oxidizes hydroxide to generate dioxygen. Hydrogen gas is generated as a byproduct. Fluorine gas can also react with oxygen to produce oxygen difluoride, the only compound where oxygen is in the +2 oxidation state. Fluoride can also participate in substitution reactions, which are driven by the extremely stable CF bond. This reaction here explains why you cannot store hydrofluoric acid in a glass bottle. The silicon in glass forms stronger bonds with fluorine, so the glass will react and dissolve in hydrofluoric acid solutions. You need to store HF in plastic bottles. This reactivity is also why HF is used in glass etching. A major difference between fluorine and the rest of group 17 is the acidity of hydrofluoric acid. It has quite the high pKa, around 3.17. Why is HF such a weak acid? HF is a bad acid because its conjugate base, fluoride, is so small and charge dense. This makes the fluoride less stable in solution and makes the dissociation of hydrofluoric acid less favored. The other halogens form much larger anions, which are much less charge dense. Because the negative charge is dispersed over a larger area, the conjugate bases of the other hydrohalic acids are much more stable in solution. Therefore, the dissociation of the other hydrohalic acids is much more favorable and their pKa values are significantly lower. Another consequence of hydrofluoric acid's weaker acidity is its increased toxicity for humans. Shown below is a very favorable reaction between calcium, a hard Lewis acid, and fluoride, a hard Lewis base. Calcium fluoride can further react with calcium phosphate to generate other fluoride salts. This is important because when you are exposed to HF, due to its lower tendency to dissociate in solution, it forms a much less polar, undissociated molecule that can penetrate the skin. Then it can corrode tissue from within, especially bones, which are made from calcium phosphate. When you're exposed to HF, you often won't feel anything at first, but then after a day or two, burns will begin to show. This is why hydrofluoric acid is so very, very dangerous. The rest of the halogens will be covered as a group because their chemistry is so similar. Chlorine, bromine, and iodine are electronegative nonmetals that are oxidizing in their elemental forms. Chlorine is a diatomic greenish gas. Bromine is a diatomic reddish liquid. And iodine is a shiny black diatomic solid. Iodine can also form a violet gas, though, and it readily sublimes. Looking at their reduction potentials, we can see that chlorine, bromine, and iodine are all fairly oxidizing, but their reduction potentials become less and less positive as you go down the group. Fluorine still follows this general trend, but it is much more oxidizing than expected. The most common oxidation states for the halides is -1 due to their high electron affinities and high ionization energies. The only time positive oxidation states are adopted is when they are bonded to oxygen or a halogen higher up in the group. Chloride is considered a fairly hard Lewis base, while bromide and iodide are considered quite soft. Because the halogens are so oxidizing in their elemental forms, they commonly react with metals or hydrogen gas to form ionic salts or hydrohalic acids. If you look back in the notes, you will see several examples of chlorine performing these reactions. But analogous reactions also occur with bromine and iodine as long as the reduction potentials are correct. If you look at the pKa values for hydrochloric, hydrobromic, and hydroiodic acid, you can see they are quite low, -9.5 to -8. This really shows how much of an outlier hydrofluoric acid really is. In organic chemistry, halides can act as both good leaving groups and good nucleophiles. The further down the group you go, the better the nucleophile and leaving group. The halogens, including fluorine, are also all capable of hydrogen bonding. In fact, a good mnemonic to remember which atoms can hydrogen bond is Hofbrinkel. For chlorine, bromine, and iodine, positive oxidation states are possible. These include +1, +3, +5, and +7. Both bromine and chlorine react with aqueous bases to form hypochlorite and hypobromite, where the halogens are in the +1 oxidation state. Please keep in mind that not all of the reactions in the notes are balanced properly. Chlorine and bromine also react with aqueous bases to form chlorate and bromate anions. Iodine does too to form iodate. Note that the stoichiometry for this reaction differs from the previous one. Furthermore, the halogens in this case adopt the +5 oxidation state. In this last reaction, chlorate, bromate, and iodate can react with water and a strong oxidizing agent to produce perchlorate, perbromate, and periodate anions, where the halogens are in the +7 oxidation state. You may notice that the ite versions of these polyatomic anions are missing. That is because they are all unstable. Even chlorite, which is the only one that can be isolated so far, is very reactive. As you may have been able to guess, these halogen-based polyatomic anions with positive oxidation states are all pretty oxidizing with fairly positive reduction potentials. The other examples of halogens in positive oxidation states are the interhalogen compounds. These are generated by mixing the elemental forms of the halogens together in different stoichiometries. The more oxidizing halogen, or the halogen higher up in the group, always acts as the oxidant, while the larger halogen, further down in the group, acts as the reductant. Depending on the size and relative oxidizing power of the various halogens, the interhalogen compounds can go up to 7 coordinate and adopt the +7 oxidation state. All interhalogen compounds are strong oxidizing agents, for the same reasons that the halogen-based polyatomic anions are oxidizing as well. A list of all known interhalogen compounds is shown below. Do you notice any trends? The 5 and 7 coordinate species involve fluorine as the oxidant. This is because you need a very strong oxidant to access the +5 and +7 oxidation states. Moreover, only iodine can go 7 coordinate with fluorine. In addition to iodine being the most reducing, this compound can form because iodine is large enough to fit 7 smaller fluorine atoms around it. This is also why iodine is the only halogen that forms a 3 coordinate species with chlorine. So not only do reduction potentials need to match up, but the size of the atoms does too. The largest member of group 17 is astatine, but almost no chemistry has been done with it because of its very short half-life, 8.1 hours. This is why it is unclear if the inert pair effect holds for astatine's 6s electrons. It just doesn't last long enough to be able to test this. The last group of the p block are the noble gases. They are extremely stable elements with full valence shells. They have very high ionization energies and very low electron affinities. They exist as monoatomic gases because they don't need to share electrons to achieve a full octet. The most reactive noble gas is radon, but not because of its chemical reactivity, but because it is radioactive. You have probably heard of radon in Kansas, especially as it's very common to test for it in basements around this area. Radon is the leading cause of lung cancer in non-smokers. The problem is not with radon gas itself, but one of its decay products, polonium, which is also radioactive. Lung cancer can develop if you breathe in radon and inside of your lungs it decomposes to polonium, which is no longer a gas. The polonium then deposits in your lungs and releases more radiation as it decays. There are very few compounds of noble gases as they are, for the most part, chemically inert. The larger noble gases, xenon and krypton, have ionization energies low enough that they can react with very strong oxidants. These compounds are often generated at high temperatures, high pressures, and are using electrical discharge. Krypton can react with fluorine to form krypton difluoride. Similarly, you can generate xenon difluoride. You can also form xenon tetrafluoride. Lastly, you can also form xenon hexafluoride. Xenon difluoride is the most stable of these species, but it is also very unstable. It decomposes in the presence of water or light. You should also note that all of these compounds are very strong oxidants, and they essentially act as fluorine plus donors. This concludes today's lecture. If anything was unclear, please feel free to ask questions during office hours or try rereading the textbook to clarify concepts. And as always, there are some useful websites and resources in the links below to help with understanding some of the concepts that were presented today.